Alright, I made this a separate video because this is a very common type of problem. Even if you're one of the easier one semester calculus classes, you still might see some integration by parts problems that have a natural log in them. And it's also really important to emphasize that, and the reason I made this a separate video is because we're going to do the opposite of what we did in the last video. So in the previous one we had x times e to the x or x times sine x, which were a couple of functions. So if you're integrating x times e to the x, or if you're integrating x times sine x, we always made the x term, so our x, or if we had an x squared, we would make that the u term in the integration by parts formula, because we want it to go away. Each time we do integration by parts, that power of x is going to get knocked down by 1. So if you do integration by parts enough times, eventually you'll end up with no x term at all, and you'll be able to integrate. But these natural log ones are a little bit different. The reason I picked x to be u in this one is because I needed, if I had made my e to the x or sine x my u, then it never would have gone away, because each time I took the derivative, it just stays e to the x. No matter how many times you take the derivative of e to the x or sine x, you keep getting either e to the x, or in the case of sine x, you alternate sine, cosine. But no matter, it wouldn't matter how many times you did integration by parts, that thing would never go away. So it wouldn't work. We'd just be making things harder for ourselves by doing integration by parts. But when you have a natural log involved, the derivative of a natural log is actually just 1 over x. So it pretty much just automatically goes away the first time you take its derivative. And that's why we're always going to set the natural log term, whatever it is, equal to u. So in the integration by parts formula, things trade places. The x term ends up being the dv term, and the natural log is the u term. So you'll see what I'm talking about in a second here. You'll see how easily this goes. So why do we have to use integration by parts on this one? Because if you want to integrate natural log of x, I don't know, I guess you have to do power rule. But you can do power rule because you don't have a 1 over x to help you. Your du would match. This x is kind of out here doing nothing for you. It's hurting you. You can't do u sub. So x times something, hey, let's try integration by parts. So I'm saying that, hey, you know what? Let's make u the ln of x term. And make dv the rest of it, which is going to be the x dx. So du, the derivative of ln of x is 1 over x dx. And the integral of dv is v. And the integral of x dx is 1/2 x squared. Alright, so now we're just going to plug and chug. U times v, which is 1/2 x squared, minus the integral of v, which is 1/2 x squared, du, which is 1 over x dx. Alright, so you can see how that paid off. There are no natural logs in this integral, which means it's now easy to integrate this thing. It's just a basic power rule. So we got a 1/2 in this first one, so we got 1/2 x squared ln of x minus, alright, so the 1 over x and x squared just cancels the x right there. So we're down to 1/2 x, so we have minus 1/2 the integral of x dx. I know it gets boring having to rewrite this first term all the time, but believe me, better that than forgetting it. Because it's a real bummer if you do integration by parts, once or twice on a particular problem. If you have to keep doing integration by parts, it's real tempting to use quote marks, or a lot of times I'll see students sort of put a box around it, to try and remind themselves to go back to it and remember to sort of put that in their final answer. But all too often, you'll forget to do that. So it's better off, you're better off just copying it down each time, even messily, than forgetting it altogether. Now watch me forget it just because I was talking while I was supposed to be doing math. All right, minus 1/2, and the integral of x is just x squared over 2 plus c. So we got 1/2. Actually, it looks like 1/2 x squared is in both terms. Times ln of x minus 1/2 x squared. Oops, minus 1/2. X squared is out there, plus c. All right, hopefully I factored that out right, but this was also a perfectly fine answer. Okay, another one. So here we've got x squared instead of x, but again, ln of x. Let's see what happens. So I'm saying, hey, we want to make u our ln of x term. Now you recall that when we do integration by parts, if this had been a sine x or something, like in the previous video, the fact that we had an x squared here means we would have had to do integration by parts twice. But I think this is going to go smoother with our making a natural log of the u term. So dv is going to be everything else, which is x squared dx. So du equals 1 over x dx again. And v is going to be integral of x squared, which is 1/3 x cubed. All right, so I'm going to plug and chug through the formula. U is ln of x times v is 1/3 x cubed minus the integral of v 1/3 x cubed times du, which is 1 over x dx. All right, so it looks like the same thing's going to happen again. This 1 over x is going to reduce the power of x a little bit. Doesn't matter. Either way, it's just the power of x, and we can use the power rule. So it's 1/3 x cubed ln of x minus 1/3. So if I cancel the x cubed and the 1 over x, that gets me x squared. So I'll just replace all this with x squared. So 1/3 times the integral of x squared, which is x cubed over 3, plus c. So that's going to be 1/3 x cubed ln x minus 1/9 x cubed plus c. Excellent. So as you can see, it only took one step of integration by parts. Because the natural log just sort of goes away on your first try every time, then just one step of integration by parts. So even though you might have guessed that, hey, if I try integration by parts, it's going to take 2 times, kind of exception to that rule is if that's only if you're making x squared your u term. But if x squared is your dv term, doesn't really contribute anything. Turns out ln x just goes away on your first try. All right, here's a fun one. Let's see. You know, remember how we said we should always try u sub no matter what? Because teachers are really big fans of sprinkling in some u sub problems to try and catch you off guard, try and confuse you, make you do a lot of work, and find out that integration by parts would not work anyway. And that's going to be the case here. Because ln x squared, I don't know about you, but I'm real tempted to use the power rule on that. So let's just try making u equal to ln of x. And then our du will equal 1 over x dx. Oh look, I've got, you know, a 1 over x dx. So I've already got my u sub set up perfectly. My du and my u already match. So there's just the integral of u squared du. Now another tip-off that you wanted to really think hard about u sub on this one was that we have this over x thing. So if you had tried to make like 1 over x dx your dv or something, then when you integrate it, you start getting natural logs, it would have been really ugly. So just rule number 1, integration by parts or any other chapter from here on out, whenever you're looking at really hard integral problems, always try u sub first, even if it's a quiz about integration by parts. Don't just assume that every problem is integration by parts, because teachers are really big fans of throwing easier problems in to mess you up, because they kind of get tired of being mean all the time and just always throwing in harder problems to mess you up. So in these chapters, because the regular problems are so hard, they start messing you up by throwing in easy problems. But of course, that's if you keep your eyes open, then that's just an excuse for you to get some easy points by doing an easy problem. All right, so integral of u squared du is just going to be 1/3 u cubed, which is going to be 1/3 ln of x cubed plus c. All right, that was excellent. Glad we kept our eye out for u sub. Wow. All right, so this one doesn't look too bad. I'm just going to do my usual rule. You know, the u sub would not work right now because if I can't just integrate. If I made this my u, I don't need the x. If I made natural log of x plus 1, this whole thing my u, then I got other problems. The derivative would be 1 over x plus 1. So u sub's not going to work on this. So I got to do integration by parts. So u equals, like I said, let's always make u equal to that natural log, whatever it is, and make my dv equal to x dx, everything that's left. So du equals 1 over x plus 1, and v, just the integral of x, which is 1/2 x squared. All right, so this is going to be the integral of, I'm sorry, plug and chug, u. It's really vu, so it's 1/2 x squared times ln x plus 1 minus the integral of v, which is 1/2 x squared du. Uh-oh. All right, now this is funky. I think you'll agree. Because the problem is, well, yeah, it's just bad. I can't really do anything with x plus 1 downstairs. So there's actually a really unusual situation, but we're going to use long division. So whenever you have an improper fraction like this, where the power of x is greater in the numerator than the denominator, that's a situation where you can use long division. And the other tip-off is that we have an x plus 1. If it had just been x, we can obviously cancel it out, but that x plus 1 means that we'll have to use long division, might get a remainder and stuff. So that's what we're going to do. So I'm going to rewrite this real quick to get rid of those 1/2s. So it's 1/2 times x squared ln x plus 1 minus, I'm just going to put that 1/2 out front, make things a little cleaner for when I come back in a second after doing long division. So long division of x plus 1 into x squared plus 0x plus 0. So x plus 1 and x squared is just x. X times x plus 1 is x squared plus x. Subtract them, we get a negative x. X and a negative x is negative 1. Negative 1 times that is negative x minus 1. And I have a 0 here, so 0 minus negative 1 is positive 1. So that's my remainder. So it turns out the answer I just got was x minus 1. So rewrite this. So we got the 1/2 x squared times ln of x plus 1. It's my opening gamut. And then I've got minus 1/2 times the integral, and this is what I'm going to replace. I just found out that x squared over x plus 1 is equal to x minus 1 with a remainder of 1, so plus 1 over x plus 1. All right, that doesn't look very pretty, except check it out. This is really just a polynomial. Integral of x I can do, integral of negative 1 I can do. This thing, this 1 over x plus 1 is just going to be a natural log. So I've got 1/2 x squared ln of x plus 1 minus 1/2. All right, now's where it gets busy. X, integral of x is x squared over 2. Integral of negative 1 is just negative x. And the integral of 1 over x plus 1 is just natural log of x plus 1. All right, so that is a mess, and technically I'd be done at this point, but I think there's some room for improvement because I've got two terms containing ln of x plus 1, and everything has a 1/2. So if I factor out, if I take the two terms that have natural logs in them, actually I should probably distribute out this negative 1/2 first, so 1/2 x squared ln. If you're bored by this, this is the last problem in this video, so you can just skip to the next video, but it's kind of some painful algebra here. Minus 1/4 x squared. Negative 1/2 times negative x is positive 1/2 x. And then minus 1/2 ln of x plus 1 plus c. Alright, so what's going on is I've got an ln x plus 1 in two different places. It's got a 1/2 x squared and then a minus 1/2. So I think I'm going to factor out a 1/2. And of course, well, ln x plus 1, I'm also factoring out. And then what's left in this first term, I factored out the 1/2 and the ln, so that means I have an x squared. And then from this one, I factored out the 1/2 and the ln, which means I got nothing except a -1. And these terms are pretty much unaffected, so 1/4 x squared plus 1/2 x plus c. Wow, what a mess. So the main takeaway on this one was that, as usual, we're going to make our u equal to natural log. Whatever the natural log thing is, that's going to be our u. But then the big trick was, unfortunately, we had to do long division, which took something that looked relatively simple. This term right here, it didn't look so simple, but it didn't look so bad either. But that just turned into a nightmare. Once we did long division, ended up with 3 different terms, integrated those, and it all worked out. But couldn't have done it without integration by parts, so, you know, thank goodness for that. In the next video, we're going to take a look at some more tricky ones, including arctangent and what to do when both things never go away. So if you want to integrate e to the x sine x dx, you're sitting there saying, hey Chris, don't we always make the one that goes away with derivatives the u term? Well, yeah, but both of these never go away. If I make my u equal to e to the x, it never goes away. If I make my u equal to sine x, it never goes away. How the heck are we going to get around this? I'll stick around for the next video to find out.